All right, good morning, class. This is lesson 13. We're covering section 3.3 today. So we're finishing up chapter 3, finishing up this discussion for different determinant properties. At this point, we've seen, how to find determinants for 2 by 2s. We've seen how we can find determinants of larger matrices using the cofactor expansion. We've seen how if there aren't a lot of zeros in a given matrix, you can reduce the matrix, modify it, and then take the determinant after, but we'd have to be careful about how we modify it and taking note of those modifications, in that some of the ways we may modify a matrix can sometimes change the determinant. So if we're trying to find the original determinant, we have to keep track of those changes so that we maintain the original determinant. 3.3 is now going to go in a slightly different direction, where we're going to look at some different applications of the determinant and how we can use the determinant to solve matrix equations. Now, before we do that, there is some new notation we have to introduce first, some notation that we're going to use in this section for 3.3. All right, so first of all, what we're about to do only works if the matrix is invertible. So the very first thing we're going to say and assume is we're going to say let A be an n by n invertible matrix, right? Because if the matrix is not invertible, what we're going to do today, the special rule we're going to create, it doesn't work, right? It only works when it's invertible. In part, this is because we need the determinant of the matrix to be not zero. Why is that so important for today? That's going to become more relevant as we continue, as we create the following formula. All right, but before we get to the formula, I want to explain where the formula comes from, and we also need to explain some new notation. All right, so what's new notation? Well, first of all, we can know, so first of all, we're trying to solve a matrix equation, which means we're talking about some kind of equation like this, right? We have ax equal to b. We would like to solve for x. Of course, at this point, we have lots of ways of doing this. One, you could take the matrix A, augment it with B, row reduce it. That would be one way to find the entries of X. Option 2, you could find the inverse of A and multiply by A inverse on the left side for both sides of the equal sign. That would work. Then X equals A inverse B. But a third methodology is the one we're going to discuss today. And in general practice, this is actually a formula that oftentimes computers use to calculate solutions for linear systems, because this is a very fast method once you understand it and once you know it. All right, so what is this we're talking about? First, let's get some notation. So let I be less than or equal to n. Why is that so important? Well, that's because we're going to be referring to one of, well, you know what, no, it's fine. We're going to be talking about pieces of this matrix A, right? But A is an n by n, so I don't have any row or column that is larger than n, right? I only have 1, 2, 3, ... up to n columns. So I need this I to be less than or equal to n, all right? So I is just some integer, and we're going to define A subscript I of B. This notation is going to be very important later in a moment. A sub I of B, where we're going to take the matrix A. These are the columns of A. But when we get to the ith column, whatever that is, when we get to the ith column, we're going to get to column I. Instead of having the original ith column of A, I'm instead going to replace it with the B column. And then ... I'm going to fill in the rest of the matrix just like I normally would, right? So A1 through AN, these are the original columns of A. All right, so how does this work in practice? Well, you can consider this example. Let's let A equal 1, 1, 1, 1, 0, 1, 2, 1, 1. And let's say B is 1, 2, 3. All right. Then A sub 2, so A2 of B means I'm replacing the second column of A. What am I replacing the second column with? I'm going to put B there. All right, so this is the matrix A2 of B. If I wanted to find A3 of B, well, now I'm replacing the third column. So the first and second column don't change. And I'm going to put B in the third column, right? So that's all this notation means. That's all, right? Now, what does this have to do with determinants? That's what we're going to do in this next step. All right, so how are we going to play with this? Well, first, I want to notice some other facts we have going on. So let me erase this example. All right, so first, let's just play with this notation and see what this means. If I have A, so right now we're just playing with the notation. So observe the following. If I have A times I of X, what does this mean? Well, I of X, this is using the same notation we have up here. I'm taking the ith column of the identity matrix, and I'm going to replace it with the X vector. Okay, so what does this look like? Well, this means in the first column, I still have the first identity column, dot, dot, dot. But when I get to the ith column, I'm going to put in X, right? This is column I, wherever it is, dot, 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 EN. Right? That's all we've done. Okay. Now, we've seen this before, where when you have a matrix times this matrix, we can distribute across the columns. And in fact, we have A times E1, A times E2, dot, 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 A times X, dot, 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 A times EN, right? Now, here's where the magic starts to happen. A times E1, this is the matrix A, times the first column of the identity matrix. All right. Now, when you do that multiplication, A times the first identity column, this is going to result in the first column of A. Why? Well, you can think about it over here real quick if you like. If I have 1, 2, 3, 4 times the first identity column, what does this result in? Well, if I do the dot product, we're going to have 1. And so, yeah, we're going to have 1, and then we're going to have 3, right? So multiplying by the first identity column is going to give you the first column of the original matrix, right? In fact, you can also see this as this is a linear combination, 1 times the first column plus 0 times the second column. So when you multiply by one of the identity columns, it's going to result in the column of the original matrix, right? So AE2, that's A2, dot, dot, dot. But what is A times X? Well, by assumption up here, A times X is the problem we're trying to solve. A times X equals B. And then we have AN here. But long story short, what have I actually written here? Well, this is AI of B. So what have we shown? We have this fact that A times I of x equals AI of B. At least this is true when AX equals B, when we have some kind of matrix equation. AI of x equals AI of B. Okay, well, that's all fine and good, but we still haven't used the determinant yet, right? How does the determinant actually help us here? Well, first, let's also highlight some other facts, and then we're going to use the determinant. So I'm going to erase some of this so I have more space. We're going to keep this fact right here, so we're going to use that in just a second. Remember this notation because we're going to keep using this a lot today. All right, so hold on to this thought. The next kind of thing we want to do is to think about, because we haven't used determinants yet, let's go ahead and use determinants now. What happens if I take the determinant of both sides of the equal sign, right? So long as I do the same thing to both sides, well, then I should get the same result. That's a valid thing you can do with equations. Right, so now we have this, and we know from our determinant properties, when you're taking the determinant of a matrix times a matrix, we can pull this apart. Okay, but now, all right, this still just seems kind of like a mess, right? How does this actually help us to do anything? Well, first, let's remind ourselves, what is I of x? This is the matrix where in the ith column, I have put x instead. So I've swapped out one of the identity columns, right? But if I'm taking the determinant of I of x, this is going to result in what? Well, we know this is going to be a, well, it can be turned into a triangular matrix, right? How can that happen? Well, think of it this way. If I have, let's just think about like for a 3 by 3. I'm going to put x in the second column. And I'm going to put, so we have like this, right? I've replaced the second column, the identity matrix, with the x vector, with the x column, right? But when I take my determinant here, I can do row reduction to get rid of x1, right? Or I could do row reduction to get rid of x3. It doesn't really matter which one you do. We could modify row 3 by taking row 3, and we want to subtract x3 over x2 times row 2. All right, what is this going to do? Well, I'm going to multiply row 2 by x3 over x2. Well, x3 over x2 times x2 is just x3. And so I'm going to subtract x3 from row 3, and I'm going to get a 0 here. So my point here is that when you have this matrix, which is almost the identity, it's so close to the identity, just in one step, we can make the matrix triangular. In fact, you can always do this. And because we can always do this, and this is a basic row reduction, it hasn't changed the determinant. What is the determinant of this matrix? Well, because it's triangular, I can multiply the diagonal. But the diagonal, because it was the identity matrix, is just going to have a bunch of ones, and the only thing that will be different is whatever is in the ith entry of x. In other words, the determinant of I of x is xi. It's going to be whatever is in that ith position of x, right? The determinant of I of x is xi. Okay, great. Now we're getting somewhere. This is where the magic happens. Because of this, what do we have? Well, now I have that the determinant of A times the ith entry of x equals the determinant of AI of B. In other words, if I divide the determinant over, which I can do, determinants are just real numbers. You can divide real numbers, right? Just like you can in regular high school algebra. Xi equals the determinant of AI of B divided by the determinant of A. And lo and behold, now we have a formula that allows us to solve for any entry of x for the equation ax equals b. We can find what that x is using this formula. This formula is called Cramer's rule, right? This is called Cramer's rule. So first of all, what do we need in order to be able to use Cramer's rule? Well, notice this rule divides by the determinant of A. If A is not invertible, that means the determinant is 0, in which case I can't calculate this at all. So this is why from the very beginning we said this formula we're about to create is only going to work when the matrix is invertible. If the matrix is invertible, then great. We can use this formula to find every single entry of x, and then we can find the solution to the matrix equation via this property. All right, but next let's actually see how this works in practice. Let's see an example. So everything I just did, no, you don't really have to memorize that. I was just showing sort of the proof for where this formula comes from, right? I didn't want to just throw this formula up on the board without any explanation. This formula, this theorem is true because of everything we just did, because of all those facts we were just talking about and writing down. All of those facts lead us to this conclusion, so we can see that this formula is actually going to work so long as A is invertible. All right, so this is Cramer's rule. So now let's see how we can use it to actually solve things. So let's just stick with a simple example for right now. Let's say we're trying to solve the system of equations 3x1 minus 2x2 equals 6, negative 5x1 plus 4x2 equals 8. I want to solve this equation, right? Well, according to the formula, x1 equals the determinant of a1 of b divided by the determinant of a. x2 equals the determinant of a2 of b divided by the determinant of a, right? If I can find these determinants, then I will know my final answer, right? Okay, I'm going to erase Cramer's rules since we have them written here now. You want to make sure you have this memorized. You're going to need that for the final exam. All right. So first of all, what is A? Well, A, we can see here, A is the coefficient matrix. 3, negative 2, negative 5, 4. B is the equals column. And So what is the determinant of A? Well, lucky for us, it's a 2 by 2. We can just use our formula for a 2 by 2. We're going to get 12 minus 10, or in other words, just 2. All right. Now we're going to need A1 of B. That's just replacing the first column of A with the B column. So that's 6, 8, -2, 4. So the determinant of A1 of B equals 6 times 4 is going to give us 24 minus 8 times a -2. That's a double negative minus negative. So this is going to be plus 16, which is going to result in 40. All right, so there's one of our determinants. A2 of B, now I'm replacing the second column with B. Again, we'll do our calculation. Determinant of A2 of B is equal to 3 times 8 is 24. Minus, again, there's a double negative, so plus 30. We get 54. So long story short, what then is our final answer? And we've done all the work we need to solve this. We have x1 equals the determinant of A1 of B, which we found is 40, divided by the determinant of A, which is 2. X1 is 20. What about x2? All right, well, x2 is going to be the determinant of A2 of B, which is 54, divided by 2, and we get 27. So my vector x, which is the solution here, is 20, 27, right? And that's it. That's all of the work you have to do here. Partly, computers use this often just because it's very fast. Computers can very quickly calculate determinants, and so trying to solve for x this way can be done very quickly for a computer. Now, of course, this is all assuming the original matrix is invertible. If this matrix A was not invertible, this method would not work. You would have to use something else. You have to do one of the other things that we've learned so far in this class, right? So this doesn't work all the time, but so long as the matrix is invertible, this is a very nice method, a very quick method. So there we go. We have this example. And if it's a 3 by 3 or a 4 by 4, you do the exact same process, right? Now, there might be a little bit more work to take the determinant of a 3 by 3, but as we've seen from 3.1, 3.2, there are ways of doing that without too much work. Okay, great. So this is Cramer's rule. Now, the rest of 3.3, there's really 2 points that I want to highlight here. The first point is, now that we have Cramer's rule, this can actually give us an alternate formula for finding the inverse matrix. How do we find A inverse? Well, we can use this to find it, and we're going to talk about how. Let's see. Let me get my water real quick. Okay, so an alternate formula for A inverse. How can we do this? Well, first of all, usually we use x as a solution for something. But now instead, let's suppose we're going to use x to build our inverse matrix. How can we do that? Well, first, let's just say, suppose that x is the jth column of A inverse, right? Do I know what that jth column is? No. I'm just saying, let's say X is the jth column. Maybe we can solve for the missing jth column. Maybe I can solve for each column of A inverse. So, okay, what does this give us? Well, then, what is A times X? Because X is the jth column of A inverse, remember the whole point of when we're multiplying A times A inverse, this is supposed to equal the identity. But when we do that dot product for a matrix times a matrix, we're doing a row of the left times a column of the right. In other words, there's a row of A times the jth column of A inverse is going to result in, that's going to fill in the jth column of the identity matrix. In other words, because X is the jth column of A inverse, A times X is the jth column of the identity. Okay, well, this seems nice, but how can this help us? Well, now use Cramer's rule, right? How can this help us? Well, according to Cramer's rule, if I want to find the ith entry of this X, well, then I need to take the determinant of AI of the equals column, EJ, and divide it by the determinant of A. But this X sub I, this was the ith entry of the jth column. So really, this is the ith column. Well, let me write this way. This is the ith row jth column of the inverse matrix, right? So in other words, for the inverse matrix, if you want to find the entry in the first column, or sorry, the first row, third column of your inverse matrix, use this formula, right? This can get us to this can fill in our entry using Cramer's rule, right? Okay, so this is nice. We can use this to find the inverse matrix. In practice, sometimes this method can be more computationally heavy. It might take a little bit longer to find the inverse with this methodology, but it can work. This is one application of Cramer's rule. Now, the notation here, personally, I think it makes more sense to leave it like this, right? The ij entry of the inverse matrix, right? That's what this is. This is the ij entry of A inverse, right? This is, if you want to find out what's in the second row, third column of A inverse, that means I is 2, J is 3. Plug this in and find your stuff, right? The textbook, however, they use a slightly different notation. I actually kind of very much dislike how the textbook does this because every semester it confuses my students. So you really want to pay attention to what we're doing here because the notation is slightly different from what you will see in the textbook for 3.3. The textbook, they use this notation where they're going to say the determinant of A, I, E, J, they're going to say this is the determinant of, and they're going to swap the J and I here. They're going to say this is the determinant of Ji, right? This is very confusing. Why are they doing this? Whoever wrote the textbook, they just thought this was nicer. It's really not. But this is what they do. They swap the I and the J, and then they don't even write the E, which is really what's happening here. You're taking the ith column of A, and you're replacing it with EJ, right? This was the notation we learned earlier. But then they call it this AJI, which I think is more confusing, but whatever. Okay. The point I'm getting at is then they give this formula, determinant of AJI divided by the determinant of A. Okay, so we can use this to construct the inverse matrix. Again, they're using this swapped notation here, so be careful with this. You can also just stick with the notation I have here. Just use this because this is much easier to read versus this is more cryptic. So be careful here. Okay. But what's the point we're getting at? Well, we can use this to fill in every single entry of the inverse matrix. Now, one thing you can note here is that for each entry of the inverse matrix, I'm always dividing by the determinant of A, right? Now, because I do that for every entry, I can just factor it out, right? Because we're constructing a matrix. So A inverse equals 1 divided by the determinant of A times, now we're doing this numerator calculation for each entry. So we have determinant of A1, 1, and then we have determinant of A2, 1. You want to be careful here with the notation. Why did I write 2, 1? Usually, this entry we would call first row, second column, right? I would write 1, 2. Well, again, remember this funniness. They flipped the I and the J, right? If you're trying to find the ij entry of x, that is the determinant of ji. They flipped the row and columns here. This is why I don't like this notation, and I think it's confusing. I think it's easier if you use this notation, then there's no flipping. But this is the formula you're going to see in the textbook. So I'm showing you both so that, hopefully it'll be less confusing. Dot, dot, dot. Determinant of A and 1, if it's an n by n, right? Which means, okay, this is the determinant of A 1, 2, dot, 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 determinant of A1, n, so on and so forth. You can kind of see the pattern here. We have determinant of A and n, and so on. You'd fill in the rest. But you can see here, again, if you're trying to find the ij entry of the inverse matrix, that means you're taking the determinant of AJI instead of IJ, right? Those I and J's flip here. So alternatively, if you want to use like the formula I have here, well, note, first of all, that A21, for example, according to what we have here, equals the determinant of A1, E2. So everywhere you see like A21, AN1, A12, you could alternatively rewrite that as A1E2, A1EN, A2E1, ANE1, right? And you could rewrite this using this notation, and then the I and J are going to be in the correct order, matching the IJ entry you're trying to fill. And then you don't have to worry about this weird messiness of flipping the I and J. Whichever way you want to remember it, that's fine. Whatever works for you, go for it. But this now gives us a formula for finding the inverse of any matrix. But again, in order to find an inverse, it has to be invertible, which means the determinant of A is non-zero. But we already knew that. Okay, good. So some other points I want to highlight here. You might see some questions in the textbook, or you might see when you're reading section 3.3, there's actually a special name for this matrix we've created here. So when we have the determinant of A factored out, this is called the adjugate of A. All right. Now, in practice, this isn't something that you're going to see a lot of the time. In fact, I'm not really even going to give you a lot of questions that ask about this. But this is still something that can pop up from time to time. In other applications of linear algebra, the adjugate can be more important, but I'm not really going to stress the adjugate very much for the sake of this class, for the sake of an introduction to linear algebra. But this can also be abbreviated as ADJ of A. This is called the adjugate. And so this gives us finally a theorem, according to all this work we've done, that when A is invertible, let A be an invertible n by n matrix. Well, then what is the inverse? Well, it's 1 over the determinant of A times the adjugate of A, which is exactly this formula we've constructed up here. Again, this notation is kind of funny. They're flipping the I's and J's, so be careful about that. Okay, right. And so this is x1, 2, which is the first row, second column entry of A inverse. Again, I'm trying to stress what this notation means because oftentimes this adjugate business confuses a lot of students. So this is what A21 is. It's the first row, second column. They flipped the I and the J, entry of A inverse, and in fact, it equals this determinant. Oh, sorry. I should have had determinant written here because we're taking a determinant. Okay. All right, enough of that. Now, the very last thing I want to discuss is a geometry application of linear algebra. So in geometry as a whole, you're probably familiar with, sometimes you want, well, if it's some kind of regular polygon, well, then sure, we have lots of different formulas from geometry that allow us to calculate the area very quickly. But what if I want to find the area of some kind of space in linear algebra? Well, how do we handle this? Okay. Well, first of all, we're going to talk about this in the 2x2 case because, first of all, it's easier for me to draw on the board, so it's easier to visualize to see what's happening. So let's say, and this is actually a theorem. It's also in the textbook if you want to read more about it. If A is a 2x2 matrix, all right, the area of the parallelogram created from the columns of A is the absolute value determinant of A. Why am I taking the absolute value? Well, there's no such thing as a negative area, right? We're only going to have a positive area. So if the determinant turns out to be negative, we're just going to take the absolute value of it, drop the negative altogether. Okay. But next, I want to talk about, why does this work? Why is this theorem true? This kind of seems out of nowhere, right? Well, imagine with me. Let's suppose A is the matrix x, 0, 0, y, right? What does this look like when I graph it? Well, x0 is, x0 is in the x-axis direction. This is a vector, right, in the horizontal direction. 0y is a vector in the y direction. Now, of course, x or y could be negative. That just means, okay, maybe the arrow is going to the left or the arrow is going down. It doesn't really matter. The point I'm getting at is, what is the parallelogram that's created from these two columns? Well, in this case, in the case of this picture, they're equal. It could be a square, but otherwise it's just a rectangle. How do I find the area of this rectangle? Well, area of a rectangle is length times width. The length of this x vector is x. The length of this y vector is y. So my area is just x times y. But what is that? Well, that was the same thing. That's the same thing as if I take the determinant of a, x times y minus 0. Now, the very last thing, I've drawn this picture like x and y are both positive, but area has absolute value, right? We're talking about a positive area. So this is why, if we take the absolute value of the determinant, it's going to give us the area of this two-dimensional space, right? Now, in fact, you can do this exact same thing for a 3x3 matrix. However, 3x3, that's a three-dimensional object. We're no longer talking about area. At that point, we're talking about volume, right? So it's not area then, it's volume. So you can use this exact same theorem to find the volume of a three-dimensional shape created from the columns of A by taking the determinant of the matrix A, right? So this can be handy for some of the questions you might see in the homework. But we can do more with this. So far we have this property, but what else can we do? Well, now, what if I transform a matrix, right? Or I transform my parallelogram. My transformation might make things bigger, or it might make things smaller. All right, so what does this look like? Well, let T from R2 into R2. Again, why does it need to be in R2? Because we're talking about a 2x2 matrix. These are vectors in R2, right? Okay. So this is a transformation. Let T be a transformation determined. So let me put a box here because we're talking about a different example. This is not this example, right? I came up with this matrix A. This is talking about this parallelogram. What I'm about to write is a different matrix A, right? Let T be a transformation determined by a matrix A. Again, what is this matrix A? It's not this matrix A. It's not this matrix A. This is just some other standard matrix that's being used by the transformation, right? This is the matrix that is used in the transformation. This is not the parallelogram. This is the matrix being used in the transformation. I want to make sure you understand this because when you see questions in Canvas, or sorry, questions in the textbook asking about these things, the matrix A is the standard matrix for the transformation. This is not the parallelogram. Okay, good. What is the parallelogram? Well, we're going to say let P be the parallelogram. Parallelogram. Did I spell that right? I think I did. Yeah. Be the parallelogram in R2. So now this is my parallelogram, and it already has an area, right? In fact, the area of P, if P is a matrix, then the area of the parallelogram is to take the determinant of the column vectors it's made from, right? But now I want to think about what happens when I transform P. The area of T of P. What happens when I transform my parallelogram? Well, first of all, you're going to have the area of P. What's the area of the parallelogram? Well, again, it's just like we did here. if your parallelogram is created from two vectors, put them together, take the determinant of that matrix, that's the area of P. Okay? But the area of the transformation of P, we have the original area, and then depending on what the transformation does, maybe T is a transformation which expands things. Maybe it's a transformation which shrinks things. Maybe it's some kind of transformation where it stretches a little bit and then skews it a little in another direction. Whatever the transformation is doing, the determinant of A tells us how much it's making it bigger or how much it's making it smaller. It's a direct scalar, right? This is all part of this theorem here. And so if you're trying to find the area of a parallelogram after it's been transformed, first, find the area of your parallelogram, and then multiply it by the determinant of the matrix being used in the transformation. This is going to give you your answer. Okay, great. Let's go ahead and transition over to today's participation question. So we're looking at participation day 12. So let's see. You know what? Actually, for sake of ease, because I'm going to use the board, I'm not going to share the screen, but you can go in Canvas and look at the matrix that's given. So this is participation day 12. All right. And then what do we have here? We're told let A be defined as below. And they also tell us right away that A is invertible, right? But how can we tell just by looking at it? Well, lucky for us, this problem gives us a triangular matrix. Because it's triangular, I know its determinant is taken just from multiplying the diagonal. And so we can see the determinant of A is just 3, right? So it's invertible right away without even doing any work. Okay, great. Now, what? We're told B is the vector 1, 2, 0, right? And we're asked to use Cramer's rule in order to solve the equation x equals b. What is x2? Well, according to Cramer's rule, x2 equals determinant of a2 of b divided by determinant of a, right? That's Cramer's rule. I've just copied it. So quite literally, this is all we have to do to answer the question. Okay, so first, what's the determinant of a? Well, we just said a moment ago, the determinant of a is 3. How do we know? It's triangular. Okay, so that's nice and easy. What about a2 of b? Well, a2 of b equals, I'm going to replace the second column with b. Now, lucky for us, this is still triangular. And so we can see the determinant of a2 of b is equal to 6. So quite literally, because we're given such a nice, well-behaved matrix, there's almost little to no work to do here. All we have to do is use our formula. So we're going to get 6 divided by 3. In other words, x2 equals 2. And that's it for today. That's all you have to put in for today's participation question. Participation day 12, x2 equals 2. All right. So that covers 3.3. We finished chapter 3 in our discussion of determinants. As we continue forward, if I remember correctly, I believe, yeah, we're going to start chapter 4 next and begin talking about what actually makes a vector space a vector space. We'll talk about vector spaces, some of the vector spaces we're familiar with. We'll talk about some of the weird kind of examples of vector spaces, which are still true examples. Talking about subspaces, so on and so forth. This is where we're moving into for chapter 4. But for today, this covers section 3.3. We finished chapter 3. So that's all for today. If you have other questions, please, by all means, do email me. Let me know. We can talk about it. Office hours begin tonight at 6 p.m. Tuesdays and Thursdays, 6 p.m. to 7 p.m. The link is on Canvas for the office hour. Otherwise, that's all for today. Best of luck, and I will see you tomorrow.